Okay, I'm very, very sorry to start a very curious or strange story. So this is the plot of average lifetime of Japanese women that is plotted against X. And you see that the average lifetime of Japanese woman at the 1970, that is about 75. But that is increasing, go up. At the 2005, that becomes 85. So do you know what is X? Yes. So that is actually the number of TV sets per 100 families. Yes. So okay, so you can laugh. Yes, you can laugh. Yes. And probably there is no direct relation between the number of TV sets and the average lifetime of Japanese women. Yes. But if something is plotted against, for example, some performance activity of something or property, and that is increasing with X, yes. And if you understand X control the performance or activity. And that today's topic is the particle size. If something, someone show the plot, something like this can be said that this is the particle size dependence, and the performance is increasing with increasing particle size in nanometer. And you can believe, yes, that can be a number of TV sets per 100 families, like something. So there is no guarantee. If you can obtain such a plot, that the performance of something is increasing with something, it is impossible to say clearly that this is really the particle size dependence or not. Then how can I do? So today's topic, my talk, is focusing on the particle size dependence. That is the material functional material like catalyst or photocatalyst or something. Those have some particle size dependence. They must depend on the particle size of powder particles. Yes, that is true. That is true. But to know the particle size dependence, I think it's necessary to use the particle of only different in size, but the same as in the other parameters. And what is the other parameters? Can we know all the parameters? And can we analyze the known parameters? And that so how many parameters should be considered? And we don't know. So in this sense, the very, very strict scientific sense, it is rather difficult to know the true particle size dependence. Yes. So for such a particle, the structural parameters, so how many that if that is minimized, only 3 parameters should be determined. One is the bulk structure. And probably if you have experience to analyze those solid materials, you think it's not so difficult to determine the bulk structure. Yes, by using X-ray diffraction. And you can determine the crystalline structure very, very easily by taking XRD, X-ray diffraction. Yes, but that is based on the assumption all the material is crystalline. If the material contains the amorphous phase, it is rather difficult to determine the amount. And also, actually, there is no way to determine the real structure of amorphous. Even composition cannot be determined clearly. And then, of course, solid material has surfaces, so it is necessary to determine the surface structure. Yes, that's right. But that is so difficult. So there is no comprehensive way of describing the surface structure. So therefore, it is rather difficult to determine. And it is almost impossible to describe. And even if we can obtain the bulk and the surface structure of a solid, we need to determine the size. So bulk structure, surface structure, and size, that is the minimal particle structure parameters. At least these three parameters must be determined to specify the particles. So without doing so, it is impossible to discuss the performance of particles. But very, very good example is here. Probably you may know the name of Titania, titanium dioxide, TiO2. One of the crystalline form, Anatase. This is the natural crystal of Anatase. That is the bipyramid structure. And this 8 facets are exposed in this octahedral particle. And the important point is that all those facets, 101, 011, 10 minus 1, 01 minus 1, and the others, all these facets are equivalent, the same structure. Yes. Therefore, the surface structure is clearly determined. And this is only one possible crystalline structure having the equivalent surface facets. All the surfaces of this particle is the same. And luckily, we could find the way of production of pure octahedral particles by hydrothermal method. And all the particles in here, this is the same SEM, scanning electron microscopic image, and all the particles are octahedral. So if we can obtain this pure octahedral particles, the bulk structure is Anatase, that is pure. And the surface structure is all 101. So this is pure. And if the size has homogeneous distribution, that can be pure. So there is very, very rare possibility of getting pure particles. And the important point is size has freedom. So the average size can be changed, keeping the bulk and the surface structure the same. So therefore, we can determine the true particle size dependence if we obtain the pure particle with different size. Chinese graduate student performed many hydrothermal reactions, and at last he got very good octahedral particles like here. And starting from the size of about 121 to 300, about 300 nanometer. All these are in XRD, that is almost 100% Anatase. No amorphous spaces there. And OAP content is studying the smallest particle has not so high, but still almost 80% OAP. And the others has the very high OAP content. That means the surface structure is all 101. And the specific surface area is from 31 to 15. And the very important point is we checked the average height of these octahedral particles and calculating the exposed area. So 8 triangles in one particle, and calculated results of specific surface area of those particles almost the same. And the important point is we could obtain pure octahedral particle in different size. Yes. And the important point is the difference in size. And actually, the size distribution is not so good, but not so bad. So all these particles has about 80% of particles are in plus minus 20% in size. So not so bad, not so good. But actually, we are trying to have more higher narrow range distribution of particles. But I think it is almost okay by using this. Okay, then to check the structure of those octahedral particles, we use the newly developed technique, reverse double beam photoacoustic spectroscopy. So I have no time to interpret in detail of this newly developed measurement system, but what I can say that by using this technique, the electron trap, that is the vacant electronic states accepting the electron, that can be filled by excitation light. And once the electron trap, vacant electronic states accept electron, they give the new photoabsorption. And the newly developed absorption is detected by photoacoustic spectroscopy. So 2 beams. One beam is to excite electron into electron trap. The other light is to be used for detection by photoacoustic spectroscopy. So by using this technique, we could obtain the energy resolved distribution of electron traps. Yes, and this is the representative results of the electron trap distribution analysis. A means Anatase, and R means router, the representative Titania crystalline structure. And if pure Anatase, only containing Anatase and only containing router, this dotted line, this is CBB, conduction band motivation, that is the same. So that is shows the bulk structure. So the dotted line shows dotted line about 3.2 electron volt, and for router that is 3.0 electron volt. This shows the bulk structure. But the same, almost the same specific surface area sample, TiO1, the TiO13, the electron trap pattern, ERDT, is completely different. So this may give the surface structure. So interestingly, the total density of electron trap is when the total density of electron trap is plotted against the specific surface area, that is not so good, but not so bad linear relation was obtained. That tells that what we measured as electron trap in this measurement is those electron traps are located mainly on the surface. And such an electron trap is not a point defect, and probably that is distributed in the surface reconstruction structure. And for Titania, the 1 electron trap per square nanometer is obtained. And then, therefore, we can say that by using this technique, the surface structure can be measured by using this technique. Although there is no, how to say, real structural data, but if the surface structure is different, the ERDT pattern must be different. So then we check the electron trap distribution for octahedral particle, these octahedral particle, and the results tells that almost similar shape in electron trap, but different depending on the specific surface area. The higher the specific surface area, the higher the total density shown in this parenthesis is 31. And this is decreasing to 18. And this is the single Gaussian fit for this ERDT pattern. And this is a bit different from the other commercial titaniums. Yes. And by the normalized at the peak position, the all octahedral particles show the almost same curvature. And that is so much narrower compared with commercial titanium samples shown in red lines. That means the surface structure is very, very uniform for OAP particle as expected. And the commercial titanium samples exposed many kinds of surface structures, including 101 facets. And this also tells the high purity of OAP sample for as the surface structure. And the electron trap density, total electron trap density is again plotted against the specific surface area, and very good linear relation is obtained. And the total the density is about 0.5 electron trap per square nanometer. That is about half of commercial titanium. So that means the pure 101, this facet contains a bit lower density of electron traps. But that depends, the total density depends on the specific surface area. So therefore, we can say that those octahedral particles has very high purity in bulk structure, surface structure, and also particle size. Then probably, so there at the present, we don't have any the clear description or clear answer for what kind of surface structure gives such electron trap. But such a surface reconstruction structure may have some coordination unsaturated site that might give the electron trap as detected. Okay, so then we check the photocatalytic activity. Probably you may know such a term, photocatalytic activity. That is, photocatalysis means the irradiation of suspension of semiconductor photocatalyst, for example, titanium oxide. The photoirradiation gives the reaction. And we choose 3 kinds of photocatalytic reaction. One is methanol dehydrogenation, that is the aqueous methanol solution. From aqueous methanol solution, the formaldehyde and hydrogen is evolved by photoirradiation in the presence of titanium oxide. And this case, the platinum is necessary to make it possible to evolve hydrogen. So in situ platinization is used in this reaction. And the second reaction is the decomposition of organic compound in aqueous solution. That is very popular in photocatalysis studies. And we use acetic acid as a substrate, and the aerated solution of acetic acid is decomposed by using titanium oxide for catalysis to evolve carbon dioxide. And the last reaction is oxygen reaction. That is the model reaction of water photolysis. And by using silver ion as an electron acceptor, the oxygen is evolved from water by oxidation. So the H2 carbon dioxide and O2 is detected to evaluate the photocatalytic activity of samples. And then this is the results. So for hydrogen evolution from methanol and the carbon dioxide production from acetic acid, there is almost no particle size dependence. The average size starting from about 60 nanometer to more larger than 250 nanometer, almost no particle size dependence, almost same activity. And so many papers reported that for those reactions, carbon dioxide production of hydrogen evolution, the smaller the better, or higher the specific surface area, the higher the photocatalytic activity. Almost all the reports tell that. But actually, by using this OAP particle, only particle size is different, keeping the bulk and the surface structure the same. In that case, no change in photocatalytic activity. So actually, there is no such a dependence. And for oxygen evolution, that is very, very interesting one. That is almost linearly increasing with particle size, not the specific surface area, is increasing with particle size. The larger, the better. So there is no such a report showing such a reversed particle size dependence in photocatalysis. This is the first example clearly showing that the oxygen evolution reaction, it is necessary to use the large sized particle. The important point is the Anatase crystalline is easily changed to rutile by heating. So that means it is rather difficult to prepare the large sized Anatase particles. So there is no chance to get the large Anatase particles. So therefore, the misunderstanding might happen. And again, the larger the particle size, the higher the photocatalytic activity. This is the first report showing that. And this must be true particle size dependent activity. So this might be the truth. Okay, so then we are succeeded in getting the particles of only different in size, but the same as in the other parameters, at least bulk structure and surface structure. Yes. Okay. So we have so many experience of measuring the ERDT pattern, and this is only the part of results of commercial titania samples, and not only titania, but also the other kind of metal oxide and carbon nitride can be measured by using this technique. And this open up the new scope of material design. Okay, so we have so many collaborators, and they sent us the samples to be measured by newly developed technique, and we are happy. I have already retired from Hokkaido University, but now I have a non-profitable organization, and you can ask me to measure your sample if you are interested in. For powder sample, minimum 100 or 300 milligram. For film on substrate, that's something like this. And please make contact with me by using these addresses. Thank you very much for your kind attention. Thank you.